Over to you, Prabha.
Okay, sorry. Okay.
Yeah, we can see your screen. Everything is fine. Yeah.
Okay, you can hear me, right?
Yeah. You can start.
All right. Okay, so thanks to the organizers for inviting me. I'm not really very well versed with the Epoch of Reionization. So what I will do today is I will focus mostly on the morphological part, and the real expert on the topic is my student Akanksha. So you can direct most of your physics questions to her. I will focus on the technique. Okay, so so I will be telling about morphological analysis of the 21 centimeter signal from the Epoch of Reionization. And this is a topic which is becoming more and more important. And there has been several papers in the recent past which tells about why this subject is becoming more important. So in order to discuss the morphology, what is needed as a starting point is imaging and tomography of 21 centimeter fluctuations. And so such data is currently not available, but it is hoped that it will become available when the big radio interferometry experiments start and data starts coming. And the data that is collected by the radio interferometers will be processed, and we will get images of the fluctuations of the 21 centimeter signal at different redshifts, which will look something like this on the right-hand side, this image that is shown here. So what is of interest, of course, are that the radio frequencies, say roughly 100 megahertz to 1 gigahertz, and the 21 centimeter redshifted signal will be seen, will be able to probe redshifts, say from current epoch to very early redshifts, say of the order of 30. So the speakers in the previous session has explained very well about the simulations, observations, and various issues, non-Gaussian issues particularly, which I will be touching upon here. Okay, so why should we bother about imaging? Of course, the reasons are that the first is that we will have direct observations of objects which are of interest. We'll be able to understand their properties. The second point, which is more relevant to my talk today, is the statistical inference of the physics that happened during this epoch, from which so far we don't have much data. So in carrying out the statistical inference, so we have heard a lot about power spectrum and bispectrum in the previous session. So also we have heard a lot about how the ionization field and the various fields of the reionization epoch are highly non-Gaussian. And hence we need to go beyond power spectrum. So this has been already explained by other speakers. Okay, so now one can, like the other speakers have done, one can think of going to higher endpoint functions, let's say bispectrum, trispectrum, and so on. But beyond a point, it is not really practical to think that we will be able to compute all endpoint functions term by term and get physics information. So it will be good if we have statistics which can capture the full non-Gaussian information, and that is where morphology comes in, morphology of the fields. Okay, so if we were to develop this as a tool for statistical inference, so we need a framework for statistical inference. So how do we do that? So we should have simulations for the various, which will give us the images, and we can construct from these simulations a framework using morphology in order to compare theory with observational data. So this is what I will be describing. So a flow chart of how we will do this is the following. So we want from these images, we want to infer physics of the EOR. So we will have on the left-hand side here, I have shown images of the ionization field as a function of time. So the different panels are showing, sorry. So the different panels, if you move down, it is showing time is going in that direction. And one can see the ionization field change evolving as a function of time. So the black regions are the ionized regions, and you can see the morphology. It's very intuitive, very simple to see that they are changing. So the question is, how can we capture this information in terms of morphological statistics? Okay, so on a very simple thing would be to count various structures, calculate their sizes, shapes of the neutral regions and the ionized regions. So I will explain more in detail in the next slide for these statistics. So these are the morphological properties. And from these, we will infer physics, which will be, I have just listed here 2 points that came to mind: properties of sources, location, kind of object, clustering, and all kinds of properties. And the second will be how reionization has progressed, time evolution. So we want to build such a framework. Okay, so before I move on to the morphological statistics, it is good to have a literature survey of what all has been done. Okay, so roughly what I could find in the literature is that the first paper using morphology for reionization, at least to my knowledge, I may not be aware of earlier papers. If you do, please let me know. So there is this paper by Glacier et al. Who looked at something called Minkowski functionals, 2006. So these are quantities which have been very well used in CMB physics to infer the statistical property of the CMB, basically to look for non-Gaussian deviations. And so these have been borrowed from there. And so these people analyzed the morphology of reionization, basically looked at the different stages of how reionization has progressed by looking at how the Minkowski functionals changed as a function of redshift. After that, there is a lot of one can see. So I highlighted the words that you can see, various words like morphology, Minkowski functional, topology, genus. These are the words that are appearing. And here you can see Betti numbers. Then two distinctions are there. You can find analysis in 3D and 2D, 2 dimensions. Okay, so these are the various papers which are there. So not so many papers have come out in the literature, but there is an increase. You can see if you go in time, you can see that there is an increase in as a function of time. There are more and more papers which are appearing. So what I will do is, so these three below are our papers, Akanksha, me, collaborators, and there is Raghu and Tithankar here. So after, what I will do is I will briefly describe what are these words, morphology, topology, and so on, basically from the lens of using these Minkowski tensors, which are a unified approach, which includes the Minkowski functionals as a subset, and which increases the information content by probing anisotropy. So that's what I will do. So I will give a general description, and then we will focus on the results that we have got in these 3 papers. Okay, so a very, very simple introduction to how we do morphology. So by the way, I will focus in this talk on 2 dimensions and not on 3 dimensions, because 2 dimensions is more intuitive, and all our, the 3 papers that I mentioned, we have worked on 3D, but the basic intuitive ideas that we build using 2 dimensions, it is easy to generalize it to 3 dimensions. Okay, so I am going to start my description by using a simple function. Let us consider, instead of random fields, we will consider a function. I have given here the sin x, sin y function, which is plotted here in some range. And what we can do is we can take level sets of this function. Okay, so it is a function in 2 dimensions. The 3rd dimension is the functional value. And what we are going to do is we are going to slice the function at different levels of the function. So nu here represents the value of the function nu, which is threshold. We call it the threshold. So this is thresholding. So if I threshold it at mu equal to half, and I consider only the regions where the field has or the function has values above it, I will get such a picture. And as I change the threshold, as I go down from the top to the bottom, so I'm going to -5, then you can see that the set has changed. So the excursion set will be the set of all points which are shown by the yellow regions here. And so the very simple thing would be to ask what is the number of connected regions. So connected region will be this yellow region. Okay. So here it's straightforward to see it is 8. And then you can ask, are there holes in the connected regions? So here there are no holes, so it is 0. Then you can ask what is the area of connected region, what is the area of holes. Then the L will be the contour, the perimeter of the connected regions and holes, and a number, 2 quantities which I represent by beta, which will represent the shape parameter. I will define this in the next slide. So these are the shape parameters. So I have given the value here. This is depending on how it is defined. So you can see that as a function of the threshold, these quantities will change. Some of them will remain invariant, will remain fixed. For example, in number of connected region does not change from these 2 thresholds, between these 2 thresholds, because of the nature of the function that I have taken. So these basically are the morphological properties that I will focus on. So, okay, here for this very trivial function, we can have a very simple, we can even calculate all these areas and lengths and so on. But it's good to have a formula for them, which we will generalize to when we have general random fields. So the number count of the connected regions is basically a count of an integral over the contour. For example, here in this connected region, we will integrate over the boundary. And kappa is the curvature of the boundary curve. So I have put C is the contour plus denotes that if I am going to integrate for a boundary which encloses connected region, I will use anti-clockwise direction. And if I am enclosing a hole, I will use clockwise direction, just to keep a differentiate. What you use, whether you use anti-clockwise, which one you choose is immaterial, but it is just to distinguish the 2. And so on. Q here represents the area. Q is the set, so it's an integral. This is an area integral, and the contour lengths will be basically integrals, and beta, the shape parameters, I will define in the next slide. So, there were many words in the previous slide on the literature. So you can see this number of connected regions and number of holes. These are the Betti numbers. And the kind of Minkowski functionals are this area of the connected regions, basically area fraction as a fraction of the total area of the space that you're interested in. Then the second Minkowski functional is the contour length, which is the sum over all the boundary perimeters, and the genus, which is the number or the difference of the Betti numbers. Okay, so these are the numbers. So now in in practical applications, we will have general fields. Okay, before I move on to that, I should define the what are the Minkowski tensors, which generalize the Minkowski functionals. These are scalar functionals. And to define the Minkowski tensor, it is very straightforward. It generalizes the previous definitions that I wrote down of the area integral, boundary contour integral, and the kappa with the boundary integral by introducing this tangent cross tangent, the symmetric tensor. I'm really sorry. Symmetric tensor product of the tangent. So the tangent, unit tangent here is defined here. If I have a boundary curve contour, then the tangent will be the tangent at each point on the contour. So I showed the n normal vector also, because equivalently we can express these in terms of the normal vector, and it will be the same. And of course, this 2 pi factor is here because when you integrate the kappa over dl, you will get 2 pi, and we want to cancel the 2 pi so that we get a count, number count. Okay, so out of these three, W1, so I can tell you that, okay, if I take the trace of these three, that is shown here, if I take the trace, they will reduce to the 3 scalar Minkowski functionals. And we can define a shape parameter from W1, because W1 will be the one which contains new information. And so if I take for any curve, if I calculate W1 and I take the eigenvalues, calculate the eigenvalues and take the ratio such that the denominator is larger, then I get the number beta, whose value lies between 0 and 1. And beta is called the shape parameter. So physically what it means, the information it contains is that this curve, I have a mapping. What W1 does is to map an arbitrarily shaped curve to an ellipse. And that ellipse, for that ellipse, we can define a shape parameter of how elongated it is by this parameter beta. So if beta is close to 1, it is isotropic. That means it's a circle. And if it is less than 1, and if it is close and it gets closer and closer to 0, it means it's getting more and more elongated. So that's the physical meaning of beta. Okay, so basically, essentially what I have defined here, these quantities capture almost all the statistics that have been used in the literature so far, apart from generalization to 3D. And so I will move on now with this definition, we'll move on to random fields. So we had a toy example, but in reality, in realistic situations, when we have random fields, for example, the matter density field or the ionization field, we will have a field which is not so nicely arranged as the one toy example I showed. And if we were to do the thresholding and look at the boundary contours of holes and connected regions, we'll get a complicated picture like this. So of course, we want to compute this for different random fields. But before we compute that, it is nice to have an analytic handle. So the nice thing about these morphological, many of these morphological statistics is that for certain nature of the random field, one can hope to calculate the expectation values of the various statistics and get analytic functions as a function of the threshold parameter nu. Okay, so for example, here the area is given by related to the complement of the error function. So it is not surprising. You can think for yourself visually that we saw in the toy example itself that it increases monotonically. It decreases monotonically as you go from high threshold to low threshold. Sorry, from low to high, and so on. Okay, so we have these. And so here it depends, the shape depends only on the threshold or the level that you have chosen, and the cosmological parameters or the spectral properties will go into this, the coefficient here, 1 by RC. So RC is like a length, is the typical scale. It sets the typical size of the structures in the field, overall size of the structures in the field. And it is usually, it is related to the derivative, the variance, the derivative, first derivative of the field to the variance of the field. So that's nice. Okay, so now let us move on to 21 centimeter fluctuations, to application. So we have seen this expression that what we will measure for the brightness temperature for 21 centimeter is the brightness temperature, which is offset from the CMB temperature. And from the various analytic expressions, it has an expression of this form. So what I am interested in is its property, fluctuating property. So I will focus on what contributes to its fluctuations. So you can see here, XHI is the ionization field. So it will change from place to place. So it's a spatial dependent quantity. So X is here is a spatial dependence. Z is redshift. I'm really sorry, my thing is moving too fast. Okay, so XH is a field. Then there is the matter density field here, which also fluctuates. The rest of the things are cosmological parameters, and we have the spin temperature here, which also fluctuates from place to place. So different physics that describe the epoch of reionization are going to go in these quantities, these fluctuating fields. And for my purpose, I'm going to simplify the physical inputs since this has been covered earlier. So the main fluctuating property or the morphology of the brightness temperature field will be determined by these three fields. So to proceed further, whatever I'm going to discuss now will be discussed from results obtained from simulations using 21 centimeter fast, which is a simplified version of probably the simulations that people talked about earlier. And so the various physical inputs can be parameterized by a few parameters. And so right now, so we'll keep the cosmology fixed. That means these parameters are all fixed. And what I describe now, I will vary the reionization model parameters. So there are two parameters here which I will discuss. One is this zeta, which is the ionizing efficiency parameter. It contains the information of how well a source of photons can ionize. And T virial, which is the minimum virial mass for a halo to collapse. So this will, which is the mass which is expressed in terms of temperature and kelvins. Okay, so we have made the simulations. First, I will discuss the qualitative features. So my goal, ultimately, what I want to talk about is how to build a framework where we can use the morphology to constrain parameters. So we'll go about that in 3 steps, of which I will describe 2. The first is the qualitative features, where I will fix the cosmology. I will fix the model parameters, fix it, and see how the morphology changes as a function of redshift. So in order to do that, I have introduced earlier various morphological parameters. So we will use, so I will fix the notation now. So we will use, what I'm going to describe now will be basically using the contour length and the shape parameter beta and the Betti numbers. So these are the quantities that I will use to describe the qualitative features. So in order to, from the L, I had used it to denote the boundary contour perimeter. So in order to change it into a size, I change it into a radius, R, so R will be the radius. And since I will be talking about two different kinds of structures, holes and connected regions, I have put an X here to denote that this X will represent either a hole or connected region. So we can, at every threshold, you can imagine that there will be a large number of structures. So we average them. This is the average quantity. And the shape is also average. So this bar here is denoting that. And so here, this will be a function of the threshold and function of redshift. So what I have plotted here is one such, So on the x-axis, I have the threshold, and the different colors of the plots are the different redshifts. And on the left column is the hole for two different kinds of structures, hole and connected regions. So you can see that in order to interpret it, so we have to match the threshold and so on. So the threshold here, I should mention that I have normalized by the variance of the field. That is why the values are of order 1. So for my purpose here, let me not interpret this, and let us condense the threshold information, and I will interpret that physically. So let's go to the next slide, where I am going to explain how I condense the threshold information. I seem to have very less time, so I have to move on. Okay, so in order to condense the threshold information, we are going to basically integrate. So we are going to choose a high threshold and a low threshold. So basically, let me explain here. So this is a different way of looking at the ionization field, and it tells you how deep the field is going. So that means the blue means is very strongly ionized. Those are the regions which have values which are larger. And as a function of redshift, you can see more and more shifting towards the fully ionized side. Okay. So how to capture this morphology? So I am going to define a characteristic shape and size at every threshold by integrating out over a certain range. So typically I will choose this characteristic size of connected regions or holes by choosing the mean value. So from the mean to the lower part, I integrate, or from the mean to the topmost part, I will integrate. Weighted integrate, because it will be weighted by the number of structures. And so this I will interpret as the typical size and the typical shape, which will be now only a function of Z. So now it is straightforward to interpret this. It's more intuitive to interpret this. So I have many plots here. Please ignore this top one, and let me start by, this is the number, the Betti number information integrated over the threshold. So you can see that there are two kinds of curves. So these are the upper ones are the holes, and these are the connected regions. So you can see that at high redshift, as the number of sources increase, as they pop up, we can see the number of the holes are increasing. And then at some point they start, holes become large and they merge. And when they merge, they lose, the number count decreases. And so there is a turnover. Okay. So that is what we see. And the similar in the opposite direction, the connected regions will be one connected region, and it will fragment and so on, and it will increase. And at some point, they will all be eaten away by the ionization process and the neutral region. And then finally, we'll be left with small neutral regions, a few of them which decrease with time as ionization ends. And similarly, this effect, the number is correlated with the size of the holes and the connected regions, and we will see this. So hole sizes will increase with time, turnover, and then become smaller, and so on, connected region. Similarly, for the beta, the shape parameter, as the mergers happen, so this indicates that merging is happening. So beta, you can see that it is decreasing as a function of time right from very early epoch, this here, 18 here. So it means that the holes as they merge, sources as they merge, ionized regions, the merging is starting from pretty early, which shows that it's a consequence of the clustering of the ionizing sources. Okay, so since I have less time, I will skip the distribution of the probability distributions, and I will move on to how can we use this to constrain model parameters. So the first thing, what I did not show, I have shown you just now only the qualitative behavior of the ionization field. And so from that behavior, by comparing it with the full brightness temperature morphology, we can find out the epochs where the brightness temperature mimics the ionization field. So that's one thing. And what I will not show here is that the statistics that I have shown, they are sensitive to these model parameters. That means if I vary the model parameters, you will see that they will change as a function of the parameters. So we can constrain them. So I will describe here a pipeline for using this to constrain parameters. So we need a mock observed data for a fiducial model, and we need the instrument noise, and we'll obtain the statistics. Then we want the morphology of the statistics in parameter space for different parameters. And then we want to carry out Bayesian analysis. So that is what I will discuss now. So we have chosen a mock data where we have fixed the two model parameters. And we have chosen a prior range for the zeta and T real. And we take simulation, a box, and resolution. So I think my resolution is maybe slightly bigger than the actual. Okay, so the first is to get the functional behavior of the statistics in parameter space. And this is the heat map of the various statistics. So these are the Betti numbers, whole connected region. This is the size, characteristic size, and this is the characteristic shape. So you can see that you can, in parameter space, as you change parameters, how they behave. I don't have too much time to focus on this, but this will be a generalization of the behavior I showed you for a fixed zeta and T real. All right. So in order to do the Bayesian inference, we have added taken the instrument noise, which is characteristic of SKA low. And rather than, so in this first step, so this is the first step of doing the Bayesian inference, we have fixed a particular redshift and we have done the Bayesian analysis. So we chose 7.4, which for our parameters, it is the place where the number of holes and number of connected regions are equal. So these are the various properties related to the noise. And the noise RMS is given here, and we'll multiply this with a 1/1/T observation to get the full noise characteristic. Okay, so for the pipeline, the first thing before we do Bayesian inference, we would like to see how what the noise does to the structures, right? Because noise can introduce a large number of small scale structures. And so these figures tell you how we beat the effect of noise by smoothing or increasing the observable time. Oh, sorry, this observable means observation time. So this leftmost panel here is a slice of delta TB with no noise, smoothed at 4.5 megaparsec. And these are the middle ones are the ones with noise, noise included, and they are smoothed, and the observation time is 10 hours and 2000 hours. So you can see if you fix the smoothing scale and observation time, clearly, of course, the noise decreases. So you can see number of structures, small scale structures are decreasing. And as you increase, if you increase smoothing, then it will, the noise will be killed. But of course, this smoothing process will introduce some bias. It will also throw away information. It will kill the small scale structures which are truly inherent in the original field. But such is life. So we cannot have the best of everything. So we have to find the optimum smoothing and the number of observation hours. So what I have described in words here are captured in this here for the morphology of the structures. And here the area is also included. Area of, so these are for poles and these are for connected regions. So this tells you how much what is the impact of noise as a function of smoothing and as for different hours. And you can see that as you increase smoothing, the statistics, the original statistics can be recovered by increasing the either number of hours or smoothing. Okay, but the smoothing that we need is fairly large. So this is around 9.5 megaparsec. Okay, so that brings me, I think, to the last slide. So this is a result of the Bayesian inference. Okay, so the stars here are the input values, input parameters of the fiducial or a mock data, and the contours are telling the 1 sigma and 2 sigma contours. And in this Bayesian inference, we have also included the mean free path distance, which I probably have not described. Okay, so the left-hand side shows us the posterior constraint and constraint for just to check without noise how well can we recover the input by the Bayesian inference. So you can see there is some bias that, for example, for this one, this is outside the 1 sigma, but within the 2 sigma. And the right-hand side is the case with noise. And the smoothing scale use is 9.5 megaparsec, and the observation time is 2000 hours. And here, so one can see that there the input model, mock model, is recovered to within the 1 sigma. So there is some increase in the error bars because of the noise on top of the cosmic variance. Okay, so these are the results for the constraint. So that brings me to my summary slide. I have, so my summary are two. I have described the morphological statistics, which a lot of people have used in the literature, Minkowski functionals. So for 2D, I focused on 2D, but one can see that by generalizing this thing to 3D, we'll have more information, but it depends on how the data will be reconstructed from the observational data. So I think that doing the analysis both in 2 and 3D have value. So Betty numbers, and one thing I did not talk about, which is there as a recent paper, is the use of moment of inertia tensor. The information content is basically the same as what I have discussed. So these are various ways of extracting, size, shape, and count information of the morphology. So they are sensitive to the physics of the EOR. So they can be used to constrain model parameters. So what is the way forward? So what I have described now is just the starting point of this enterprise. There's a lot of work to be done. There are several to build it up as really a technique where we should be ready to apply this to observe data, the several directions. So we have to understand the various biases. For example, I mentioned that smoothing biases the statistics. So we need to do better understanding. We have only just started understanding. Then these different statistics, what is the information content of the various statistics? How do they complement each other? So these detailed analysis need to be done. And the third thing is that I have not discussed about foregrounds. The assumption is that everything is nicely subtracted. There is no foreground. Of course, residual foreground will bias. Then we will use multiple redshifts and the full threshold range. So I have integrated out the threshold in order to simplify the intuitive physical interpretation, but we may lose information in doing so. There may be physics which can depend on this, so this should be done. Then a comparison of these various statistics, the ones which are in the endpoint functions and these integrated quantities, how do they compare, or the constraining power, and how do they complement each other? So I think the way forward is to use them together in a complementary way to maximize the constraining power. And of course, the realistic model of EOR, what I have described, is very simplistic 21 centimeter fast simulations. So we should be doing this on realistic models. So that's the end. Thank you.
Thank you, Prabha. Very interesting and in a way alternative way to constrain EOR. So we can take some questions. Rajesh, I think, has a question. So Rajesh, you can unmute yourself and ask your question. If there are any questions, you can use the raise hand option. I think Rajesh has a question. Okay. Yeah, ask your question.
So there are two questions basically. So one is, so we showed in the previous slide. So it seems that the constraint without the noise.
Rajesh, you are not audible. There is a lot of disturbance.
Sorry.
There is a lot of you are not audible.
Hello.
Yeah, now you are.
Yeah, now it's better.
Okay. So my question is, you showed in your previous slide, it seems that the constraint without noise is more biased than the with noise. So it is bit counterintuitive, right?
Yes, that's correct. Yeah. So there has
what
to
is
be
the reason?
Yeah, there has to be some bias because of the smoothing, effect. Apart from that, it's not really clear to me what can be causing. So I don't think we have isolated whether what happens with the noise, small scale structure, whether that is having any effect. So this has to be understood. So there is, yes, you're right that there is seems to be more bias, but I think we have not quantified it properly as yet. That's why I mentioned it in one of the way forward points.
And another small question, like people have claimed that the Betti number provides a more useful description of the topology than these things, the other like genus and like Euler statistics. Now the question is, which one is the most general quantity one can calculate?
Again, Rajesh, in order to answer your question, your questions are all here. I have said that we have to compare the information content of various statistics. So we have not done that as yet. So we have just about started the.
I'm talking about from the theoretical aspect. So which one is the most general? From that we can derive anything.
Okay. So what I can tell you at the moment is that, for example, if I were to compare, let's say, so I have listed here, you can see various statistics. So if I were to compare genus and Betti numbers, so the genus is basically a subtraction of the two Betti numbers. And in doing so, we do lose information. So this I had shown in one of my papers for the CMB, how much information we lose, okay? So if I were to compare genus and Betti number, yes, there will be loss of information, and it depends on how much non-Gaussianity is there. So if it is very largely non-Gaussian, then the information loss is more. Okay. Then it is meaningful to compare. Sorry.
No, it's okay. Yeah, go ahead.
Yeah. So the next thing is one can compare Minkowski tensors with scalar Minkowski functionals. And in doing so also, we lose information. Again, because the Minkowski functionals are trace of the Minkowski tensors. So you lose the 2 degrees of freedom, you combine it to 1, but the errors don't always give you double the information. but it'll go down as square root of how many Minkowski tensors you are averaging out to get the scalar Minkowski functional. So if you go from 2D, for 2D, if you do tensor to scalar, the gain will be like a factor of 1/√2, and if you have 3D functionals and tensor, it'll be like 1/square root of 3. Okay, that's the amount. That's the very basic estimate one can do. But when you have noise, of course, there will be change in these properties, and so that is the part that we have not studied properly. Okay, that needs to be studied further. So yes, there is gain of information when you go from some statistics gain. That is why in these 3 papers that we have used, especially in the last one, we have used all the information. We have not used just we have used all the information in the Minkowski functionals, and we have used the tensor and the Betti numbers.
So Rajesh, so to answer further, we had done a comparison of separately Betti numbers, Minkowski tensors, etc. So due to the physical behavior of these fields, we find that if we use Betti numbers in combination with Minkowski tensors, we gain more information as compared to when we use Betti numbers alone. So while Betti numbers in itself gives more information, but the combination will give even more information. So that's why we are using all the statistics here.
Yeah.
All right. So I think I will take one quick question. If Kanan has a question, I think. So just one quick question before we move to the next talk. Kanan, do you have a question, or you want to take it to the discussion, or if it's a quick question, we can take it. Yeah, Kanan.
A lot of noise. Okay, so can you hear me clearly?
Yes, I can hear you.
Okay. Hi, Prabha. So I just one simple question. When you smooth your simulation, do you also do it along the line of sight direction, or you just do it in 2D?
So I think Akanksha should answer this, but I'll answer what I think is the answer. So we are doing only we are doing slices, and this is in co-moving space. So we don't have any light cone effect. We have not taken care of that.
Yeah, because
so right now we are just using one frequency channel, and we are just taking one single slice. And when we are constructing that slice, then we are taking it as an average over a frequency channel, single frequency channel.
Right. Now I'm asking because I saw that you have assumed your bandwidth to be 1 megahertz.
Yeah.
So I think your frequency direction smoothing should be of the order of that, right? Because
yes.
So you have to.
So we chose the channel width to be the same. Like we take a 1 megahertz slice, and like we take frequency channels like this smaller frequency channels, and we average over a 1 megahertz this thing. So we average, we don't take into account any physical or any other line of sight effect.
Okay. Thank you.
Okay, so we can take some more questions in the discussion. Thanks, Prabha, once again.
Okay, yeah, thank you.
Yeah, so our next talk is by Aadarsh Pathak from IIT Indore. So Aadarsh, you can load your slides and can start.
Hello.
So I'll send you at 15 minutes.
Okay. Can you hear me?
Yeah.
Okay, thank you. Hello everyone, I am Aadarsh Pathak. I am a second year MSc student at IIT Indore. In this talk, I am particularly going to talk about the current project which I am doing, whose title is using the largest cluster statistics on 21 centimeter to constrain reionization models. So I can essentially start with this picture. Here we can see the Big Bang on the left to the current scenario when present stars and galaxies can be observed. My research interest basically lies within the CDOR era, and we all know that this is the phase when first neutral atoms formed, and at later stage they ionized by the ionizing sources. Now, in order to probe the CDOR era, we have several direct and indirect methods, but the most promising direct method is to probe the neutral hydrogen. And why it is so? Because when we are looking at this universe constituent, we can see that we have less than 5% of them is basically the normal baryonic matter whose properties are actually known to us. And out of this 5%, we have almost 75% of them is the neutral hydrogen. So if you are probing this neutral hydrogen, that means you are probing a very large chunk of our visible universe. But the question is, how can we do that? So for that, we have essentially the 21 centimeter line emission from this neutral hydrogen when basically spin flip takes place at the ground from the ground state of the neutral hydrogen atom, which we all know. Now, if you are talking about the reionization, and then there are several sources which can affect our ionization in one or more different way. So on the basis of this, we are basically classifying the 4 source models, which we can see here. The first and fourth source model is known to emit ultraviolet photons emitted from the galaxies residing in the dark matter halos. And here we are particularly assuming that the number of ionizing photons emitted by them is basically is proportional to the nth power of the halo. So for the first case, we have n is equal to 1, and for the last one, we have n is equal to 2 or 3. The middle two are known to emit hard X-ray photons and soft X-ray photons respectively, which are creating uniform ionizing backgrounds. So once we have these 4 source models, we can basically use them to define our 6 reionization scenarios, which we can see here. These 6 reionization scenarios are using these 4 source models in different ratios of proportions to define them. I am particularly using these 6 reionization scenarios adopted by Mazumdar et al. 2016 to basically see the evolution of my largest ionized region. Here I have shown the result for 21 centimeter brightness temperature map for 6 different ionization scenarios taken from Mazumdar et al. We can see clearly that the topology of our 21 centimeter signal is quite different for different ionization scenarios. And even if you are pointing towards the particular phase transition when the different isolated regions basically coalesce together to become the large interconnected region, which is particularly known as percolation. This is also different for different ionization scenarios. So we are actually interested to see that whether we could analyze this kind of behavior with the evolution of my LCS statistics or not. So for that, I'm using the largest cluster subgen 2 algorithm, which I'm showing here. This algorithm is basically used to determine the shapes and size of my ionized region. And it is based on FOF algorithm, which particularly accepts a threshold value and a minimum group size. And corresponding to that, it basically identifies the shapes and size by calculating the various Minkowski, the 4 Minkowski functionals, which I'm showing here. These 4 Minkowski functionals is basically known to give the geometrical and topological shapes. And since the subgen 2 algorithm which I have discussed, it is basically using the triangulation technique in order to identify the clusters. So we can define our 4 Minkowski functionals in terms of triangles. So the first Minkowski functional is the surface area, which is basically the sum of all triangles which has been marked from the given cluster. My second Minkowski functional is the volume, which is the volume of all tetrahedrons, which are ultimately being formed from the triangles which I discussed earlier. The third Minkowski functional is the integrated mean curvature, which describes about the concavity and convexity of our shape. And the fourth Minkowski functional is the integrated Gaussian curvature, where we are extensively using Euler characteristic, which defines the topology of our object. So that if we have different geometrical shapes, if I have the same Euler characteristic, we can say that it could have the same topology. So these are the 4 Minkowski functionals. Now, once we have these 4 Minkowski functionals, we can basically use them to define our 3 shape finders as thickness, breadth, and length. These 3 shape finders can again be taken in different ratios to define our 2-dimensionless quantities, which are planarity and filamentarity. These 2 quantities can basically describe our topology, that whether we could have a planar, filamentary, a spherical, or even kind of topology. So these are the shape finders which is being used in the subgen 2 algorithm. So in a nutshell, what I'm actually doing, I'm basically using the simulated H1 21 centimeter map from different ionization scenarios. And then I am applying the subgen 2 algorithm on them. And by using the shape finding technique, I am evaluating the values of LCS and seeing the evolutions. So based on this, what are the results which we have obtained? Let us discuss them now. Here I am showing the variation of neutral fraction with the red shift. This reionization history is going to be same for all reionization scenarios which I have discussed so far. Now let us concentrate on this first result. Here I have plotted the LCS, that means the largest cluster statistics with the neutral fraction and the filling factor. Largest cluster statistics is basically the ratio of the volume of my largest ionized region with the volume of my all ionized regions in our simulation box which we are taking. And filling factor, I'm sorry if you're not able to see this. Filling factor is basically the ratio of the volume of all ionized regions, including my largest one, with the volume of the simulation box which we are considering. So when we are concentrating on the leftmost figure, we can see that I have plotted a result for the fiducial case. We can see that for the point before percolation, here the vertical line shows the point of percolation. Before percolation, we have a very small value of LCS. But after percolation, it increases drastically. That means if you're looking at it physically, then we can see that before percolation, we have a small ionized region. At percolation, it increases, there is a significant increase, but after percolation, we can see that my entire simulation box is almost filled with this largest ionized region. And when I'm plotting this LCS with the filling factor, we can conclude the fact that before percolation, we have a very little contribution of my largest ionized region in the simulation box. That means the contribution of LCS in filling factor. But after percolation, it has become dominant. This same kind of behavior has been obtained for all other reionization scenarios as well, which we can say here that the same kind of trend has been observed. And the interesting thing is that all these reionization scenarios, most of them are basically percolating at different reionization scenarios and different neutral fractions. So basically we can use this percolation and the evolution of LCS to distinguish between the different reionization scenarios. And we can do one more interesting stuff here, that the reionization scenarios which are basically percolating at higher neutral fractions, we can group them in inside-out reionization, mainly by scenarios like fiducial clumping, PLN is equal to power law, n is equal to 3. And the scenarios which are percolating at lower neutral fractions, we can group them in outside-in reionization, mainly by UIB dominated and SXR dominated. So this is one of the another categorization which we can do. For the check of our consistency, we have basically plotted the bubble size distribution for 6 reionization scenario, although I'm showing here 2. At the leftmost figure of both this figure, I am showing the point at percolation, and as we are reaching towards right, my neutral fraction is basically decreasing. We can clearly see that at percolation, it is very difficult to distinguish between the largest ionized bubbles and another bubbles. But as we are approaching towards lower neutral fraction, my largest ionized bubble is quite distinguishable as compared to the other, which is very much consistent with the LCS evolution which we have seen. Now this result I have already discussed for the fiducial, but for the completeness, I am showing here the result for other reionization scenarios. We can see that for before percolation, we have a very little contribution of LCS in filling factor for all reionization scenarios as we observed in fiducial. And after percolation, we can see that my LCS contribution in filling factor is most dominant and is most significant for all reionization scenarios as expected. Now here I plotted the number of isolated clusters in log scale formed by different reionization scenarios with the neutral fraction. We can see that initially we have the increasing ionizing number of isolated cluster, which reaches its maximum at percolation. And after percolation, since we know that most of them will basically coalesce, so they decrease once again. Particularly if I'm talking about the scenario like UIB dominated, then it has the largest number of isolated cluster as compared to the scenario like PLN is equal to 3, which has the least number. But at the same time, they are forming the largest shape of ionized cluster. This result, here I plotted the number of isolated clusters in log scale with the filling factor. Here also we can draw important conclusion that for the scenario like UIB dominated and somehow bisects are dominated, that means which are mostly following the outside in, we are having the very low value of filling factor as compared to the scenarios like PLN is equal to 3 or clumping. which are having the larger value of filling factor. That means at the end of reionization, you can expect that my entire for my simulation box, most of the volume will be covered with the largest ionized region, or with the ionized regions. Secondly, if I'm plotting this filling factor with the neutral fraction, we can see that for inside out reionization scenarios, that means the reionization scenarios which are following the inside out, we can see that we have a significant contribution of filling factor in my entire neutral fraction range. But for the outside in reionization, we have this contribution of our filling factor only after certain neutral fraction, which is basically the percolation. Now here I have plotted the result for the log shape finders which we have obtained. So here I plotted for the result for the largest ionized region, as it is the main thing of our consideration. So when I plotted the cross section and length variation with the neutral fraction and volume, we have obtained the plot like this. One noticeable thing is that here I plotted the length in log scale, while the cross section here is in the linear scale. So we can see that as we are approaching towards lower neutral fraction, our length is varying significantly as compared to the cross section, which almost remains constant. That means there is a one-to-one correspondence of length with the volume. So we can say that mainly after percolation, we can observe filamentary kind of topology for our fiducial scenario. And this is not only limited to the fiducial, but the same kind of behavior has been observed for all other reionization scenarios as well. Here I have plotted the cross section and length separately with the neutral fraction. We can see that the length is cross section is not varying a lot, but the length is varying significantly, and it is order of magnitudes higher than the cross section. So we can say that after percolation, most of these reionization scenarios are going to follow the filamentary topology. Here I plotted the planarity, filamentary planarity in genus with the volumes, where volumes are basically taken in beams. We can see from the figure, that as we are approaching towards higher neutral fraction or higher volume beams, we are having basically the increasing filamentarity, and the planarity is not changing a lot except of this model, clumping model. So we can conclude that we could observe a filamentary kind of topology for all reionization scenarios. One noticeable thing is that this result I plotted for the case just before percolation. So we can say that before percolation also we can obtain the filamentary kind of topology for most of the reionization scenarios. And genus variation with the volume basically describes the multi-connectedness of the different ionized regions with the volume. So we can see that basically few of the reionization scenarios are basically showing the large multi-connectedness, while the others are not showing so much, like UIB dominated. So basically in this way we can categorize them on the basis of the evolution of topology also. So finally, what we can conclude that we have the largest cluster statistics, which we can use to differentiate between the different reionization scenarios. We can also differentiate between the inside out and outside in reionization on the basis of Celsius evolution. For the check of consistency, we have used the bubble size distribution, and we have found very much similar kind of results. And importantly, the reionization scenarios mainly after percolation is showing filamentary kind of topology. That's all from my side. Thank you.
Thanks a lot, Aadarsh. Very nice talk. If there are any questions, you can use the raise hand option or use the chat box. Yes, Deep.
Yeah, Aadarsh, I just wanted to understand whether you have thought about whether the distinguishability of different reionization models will be possible in actual data, where there will be noise, you won't know it will be mean subtracted, and it will probably also be smoothed. So how well will it work there?
Okay, we are actually planning to do this next. This is our next approach, to add some noise and see how our LCS will behave. So this is our next approach.
What about mean subtraction? Will that matter in this case?
We haven't do this. We can probably look at this later. I haven't do this. No.
Okay, yeah.
Okay, if there are no other questions, we can go to the next talk. Thanks, Aadarsh, again. So
Okay, thank you.
The next talk is by Fazlu Rahman from IIA.
Hello, can you hear me?
Yeah, so you can use, you can log out. You can unshare the screen, Aadarsh. The next talk is by Fazlu. Yeah, so you can load. Yeah, thanks.
Hello, can you hear me now?
Yes, yes, you can start.
I hope my screen is also visible.
Yes, 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 you can start.
Okay, hello everyone. Yeah, thank you for the organizers for giving me the opportunity to present my work here. So I'm Fazlu Rahman, a PhD student at Indian Institute of Astrophysics, Bangalore. So today I would like to discuss the recent work that we have done on the nature of non-Gaussianity and statistical isotropy of the 408 MHz Haslam synchrotron map. So a archive version of this work is recently published. So mainly this work is mainly done in the context of CMP, but the results are interesting for EOR experiments also. So this work is done under the supervision of my supervisor Pravabati from IIA and my collaborator Tuhin Ghosh from NICER. So here is the outline of my talk. I would like to start with the galactic foregrounds for CMB and the analysis of synchrotron that we are doing here. So I'll briefly explain the tools that we use, Minkowski functionals, which has already covered by Prava in her talk. So in the later part, I will explain the pre-processing steps that we do and analysis and results, and I'll conclude with a summary and discussions. So galactic foregrounds. So we know that galactic emissions have been a severe challenge to detect CMB signals. The story is the same with 21 centimeter EOR experiments also. So in the context of CMB, we can see that the plot indicates that so for different Planck frequency bands, which is shown here in vertical bands from 30 to 857, you can see that apart from the CMB which is shown by cyan color, we have various other emissions. So in the mainly in the low frequency part of the CB black body, we have galactic synchrotron emission, which is caused, which is mainly dominated coming from the interaction of the relativistic electrons with the galactic magnetic field. Apart from that, we have thermal dust emissions in the high frequency bands, and also we have spinning dust emissions because of the nano-sized dust grains. We have free emissions, we have line emissions such as carbon monoxide, etc. So the left portion, the left plot, which is given by the Planck collaboration, indicates the RMS brightness temperature. However, for CMB, the right plot indicates the polarization. So we can see that synchrotron emission as well as thermal dust emission is again posing a severe challenge for detecting CMB polarization. So we know that the CMB B modes is it's a long-term dream for us, which indicates the details of the imprints of the primordial gravitational waves. So we know that these galactic foregrounds are posing a very serious challenge for the detection of these very tiny feeble signals. So the point is understanding the properties of these emissions is crucial to develop and improve the component separation pipelines. So what we are doing in this work is we study the statistical properties of one of the major galactic foreground, namely the galactic synchrotron emission in this work. So now I would like to highlight what is the relevance of these statistical properties. So here in this work, we are actually focusing on the non-Gaussianity and the statistical isotropy of galactic synchrotron emission. So the main motivation is like this. So in many of the foreground modeling, these emissions are assumed to be Gaussian random fields, and they are following statistical isotropy at small scales. So even though this assumption or this approximation is taken on the basis of the case that it will simplify the calculations, we don't know the physical motivation for the assumption. So the main motivation of our work is to check whether the assumption of Gaussian random field and statistical isotropy for galactic synchrotron at small scale is valid or not. So intuitively, if we think, we know that galactic emissions are highly nonlinear, and there is no point to think that, okay, these are Gaussian fields, but in small scales, this assumption is taken. So we need to check the validity of them. Apart from this main motivation for our work, we have other secondary motivations, such as that understanding the statistics will help us to check or to probe the residual contamination in clean CMB maps. Also, precise quantification of foreground non-Gaussianity is important for the detection of the primordial non-Gaussianity. And we are also interested in the astrophysics of these galactic synchrotron emission and the underlying magnetic field. So all these are our secondary motivation for studying the statistical properties. So how are we doing this? The analysis of galactic synchrotron emission. So we are studying the Gaussianity and statistical isotropy of synchrotron emission from our galaxy. So for this, we use the reprocessed version of the Haslam 408 MHz all sky map. So this reprocessing is done by Matthew Ramaze in 2015, and this is a map which is widely used as a fiducial map for the content separation. So previously, Ben David et al. In 2015, they have already shown that Haslam map is Gaussian for patches of size 3.7 degree based on skewness and Curtis studies. Also in 2018, Rana et al. Has shown that the bispectrum analysis indicates that the Haslam map is Gaussian at small scales, at scales less than 3 degree. So the rough calculations with scalar-Minkowski functionals were also done in their work. So here in this work, what we are doing is we are trying to do a thorough analysis on the statistics of Haslam map using Minkowski functionals. So I would like to give you a brief review of Minkowski functional. A detailed description was already given by Prava. So I would like to remind that Minkowski functionals are the geometric and topological tools. So they are used to study the statistics of any random field. So mainly we probe the non-Gaussianity of the field, and Minkowski tensors can help us to study the anisotropy information in the field. So the extra advantage of using Minkowski functionals over the commonly used tools like skewness, bispectrum, etc. It's like they carry the details of all the higher order correlations. So for fields which whose nature is unknown, like the foreground field, Minkowski functionals are best suited. Another second advantage is that unlike bispectrum and trispectrum, these are computed in real space. So we know that Minkowski functional follows escalation set formalism. So given a 2D random field, like a CMB Gaussian random field given here, so we can create escalation set with different threshold values, nu equal to -2 to nu equal to +2. So these are the different threshold values, different escalation set obtained from this 2D random field. So for these different escalation set, I can calculate various statistics, various quantities. So we can calculate the area of these structures, contour length of these structures. We can calculate the number of yellow regions, which I denote as beta1, number of holes or the black regions, also genus, which is the difference between the number of connected region and holes. So these 3 out of 5 quantities, these 3 are the scalar Minkowski functional. So a mathematical definition of them are given as like this. So how are scalar Minkowski functionals helping us to probe the Gaussianity of the field? That is the question. So as Prava has already shown, so Tomita in 1986 has given the analytical expectation for Minkowski functionals for a Gaussian random field. So for V0, it follows a complement error function. V1 is a Gaussian function. And V2 is a first order, is a H1 Hermite polynomial, nu times e to the power minus 1 square. So the point is that scalar Minkowski functionals can be used to test the Gaussianity of any random field. So now we will come to the tensor generalization of these scalar Minkowski functionals. So we have 3 Minkowski tensors, W0, W1, and W2. And out of this, W1 contains extra information. So W1 is the tensor generalization of contour length. So as it was already shown that the trace of W0, trace of W1, trace of W2, they gives the corresponding scalar Minkowski functionals. But here we are interested in the W1, which is the contour Minkowski tensor. And what is the extra information that they contain? So they contain the information of the alignment or the direction. So as already shown by Prava, so we know that the ratio of the eigenvalues of W1, which was the beta in her case, so that gives the directional information. But in this work, I'm interested in another quantity, which is denoted by alpha. So this alpha is the quantity which indicates the average isotropy of the field. So we can see that if for multiple curves, we can calculate this W1. and we can again take the eigenvalues lambda1 and lambda2, and we can take the ratio of that. So alpha is defined as lambda1 over lambda2. So the definition is like this. So if the distribution is statistically isotropic, alpha value will be equal to 1. And if the alpha value is less than 1, that implies that there will be a particular direction or particular alignment for the structures in the field. So given these two details, so I would like to extend a little more on the analytical expectation for the Minkowski functions. So as already discussed, the expression is given by Tomita in 1986 for a Gaussian random field. So V0 is an error function, V1 is a Gaussian function, and V2 is a new times Gaussian function. So this is the case for a Gaussian field. Now for a mildly non-Gaussian field, such as a CMB field, where we know that the perturbative expansion is valid over a Gaussian field, we can expand the Minkowski functional as a power series over sigma. So the Minkowski functionals Vk can be expanded over its corresponding Gaussian Minkowski functional plus a first order term and a second order term and higher order terms. So this is the analytical Minkowski functional for a mildly non-Gaussian field. So now what are these first order, second order terms? So I don't want to explain all the terms here, but these are the first order terms for V0, V1, V2. So if there is a typo here, this is V1 and V2. So for V0, V1 and V2, we have different combinations of Hermite polynomials, and we have S0, S1 and S2. So I would like to bring your attention for these three parameters, S0, S1 and S2. These are the skewness parameters, generalized skewness parameters, which are given by these combinations of field and their first and second derivatives. Now, what are the second order terms? So second order terms are given by these expressions. But again, I would like to bring your attention for these different terms here, S0, S1, S2, K1, K0, K1, K2, K3. So apart from the three skewness parameters, in the second order terms, we have K0, K1, K2, K3. These are the four generalized kurtosis parameters. So the point is that first order term contain only skewness parameters, and the second order term contains skewness as well as the kurtosis parameters. So what is the motivation of doing this analytical expectation for mildly non-Gaussian field? So this will actually help us to understand the nature of non-Gaussianity. So even if we say that, okay, given a field is a non-Gaussian, whether so we need to probe what kind of non-Gaussianity it is. Like in the case of CMB, we have inflationary model predict different types of non-Gaussianity, like local type non-Gaussianity, which are parameterized by FNL and GNL. So for this kind of non-Gaussianity, people have actually calculated the deviation delta of various Minkowski functionals as a function of threshold. So you can see that the plot that I have shown here is the first row. So the columns indicates different Minkowski functionals, and the first row indicates delta V0 normalized by V0 G max for FNL 100. So if the non-Gaussianity is dominated or it is sourced by FNL, delta FNL will have such a characteristic shape. If it is sourced by GNL, then which is the second order term, so then the shape of non-Gaussianity is given by shape of Minkowski functional is given by this. And if the non-Gaussianity is sourced by both FNL and GNL, then it has a delta VK has a characteristic shape. So the idea is like this: the shape of delta VK can shed light on the nature of non-Gaussianity. Okay, so I would like to, I don't want to discuss in detail about the methods. If you're interested to know, later we can discuss. So we use the field values to calculate the Minkowski functionals. So we also have a geometric approach also. So given the time constraints, I'm not going into the details of them. So we also do some pre-processing steps. So first thing is, we know this is the full all-sky Haslam map. In the galactic region, we can see that there is a very high emission. So we need to mask those very uncertain regions. So we use different kind of mask. So one mask that we use, so the mask is parameterized by the number called UCut. So we use various UCut values ranging from UCut equal to 60, UCut equal to 30, 40, etc. So what does this UCut number implies? So UCut implies that all the field values greater than UCut will be masked. So you can see UCut 60 implies that the galactic central region is remote and it has a sky fraction of 74%. And we also have used in the right, I have shown the sky fraction as versus UCut. So we have used 5 UCut values ranging from 60, 40, 30, 25, and 22. And you can see that what is the, how does the map look like for UCut equal to 25. So UCut equal to 25 has a sky fraction of 41%. And apart from that, we are interested in the behavior of the field at different angular scales. So for this, we use something like a bandpass filter. So this is applied in the Fourier mode. So we can see we use a Tanash filter, which is given, which has a form like this given here. So the angular scale multiple cut is parameterized by L cut. So when I say L cut equal to 30, that implies that I'm only interested in the features having in the structures with size less than 6 degree. So we know that L is related to theta by this relation approximately. So L cut 60 implies 3 degree and L cut 90 implies 2 degree. So visually you can see that if I increase the L cut values, the size of the structure is actually going down. And in order to quantify the statistics, we also have Gaussian isotropic simulations. We have used these. We have obtained the Haslam full angular power spectrum of Haslam map, and we have produced 1000 Gaussian isotropic simulations using PolSpice. So I would like to come to the analysis and result. So before going to the analysis and result of Minkowski functionals, so I would like to show the results for skewness and kurtosis. So I would like to again remind the expressions for skewness and kurtosis. So we have 3 skewness parameters and 4 kurtosis parameters. Now, another thing I would like to stress here is that we also have another parameter for masking, which is SM. So even though we know that we use different masks, which are binary masks, so in order to get rid of the boundary effect, we have already smoothened those masks. So 25 Kelvin U-cut mask is given like this, but this is not a binary mask, it's already appraised by 5 degree Gaussian smoothing. So just in order to move again away from the contaminated boundary effects, we stay away from the boundary pixels, which is parameterized by SM. So what does SM imply? So we know that is a smoothed mask means all these blue regions implies 0 and red regions implies 1, but there is a transition from 0 to 1. So I say, when I say SM equal to 0.5, I say that I'm only interested in the regions having the mask values greater than 0.5. So increasing the SM values implies that I'm again moving away from the boundary regions, which means that I'm being more conservative and saying that I don't want to have any contamination in my result. So we have actually used different values of SM. We have tested our results, and we have fixed to SM equal to 0.9 in our Minkowski functional calculations. So quickly, I would like to highlight the skewness and kurtosis results, which are shown here. We have 3 skewness parameters and 4 kurtosis parameters. So throughout this presentation, the red implies U-cut equal to 60 Kelvin and green implies U-cut equal to 25 Kelvin. So first, I would like to highlight that what is the behavior of the results with respect to SM. So we see that at lower SM, at lower L-cut, the cumulants show large variations with SM. So the different lines, dotted, dash, and full line. So these imply different values of SM. So we find that this SM has significant effect on lower L-cut value or larger angular scales. But however, we see that at L-cut equal, at higher L-cut, we see a convergent behavior. So for our later calculation, we fix SN, this S nu or SN to be 0.9. Now I would like to highlight the skewness and kurtosis result. So we can see that these skewness and kurtosis results are actually plotted as a function of L-cut, which is the angular scale. So all 4 values of the kurtosis are larger than that of skewness for both U-cut and L-cut. Second thing is that the skewness values shows clear decrease with increasing L-cut, and all kurtosis values also decrease by decreasing U-cut as well as increasing L-cut. So what does this imply? This result shows that the non-Gaussian nature of the Haslam map is predominantly sourced by kurtosis terms, since the kurtosis values are larger than the skewness terms. And apart from that, since we see that the skewness and kurtosis values are actually decreasing with higher L-cut or lower angular scales, so we find that at smaller angular scales, the field shows convergence towards Gaussian behavior. So now we'll come to the scalar Minkowski functionals. So I have shown the 3 scalar Minkowski functional V0, V1, and V2 for L-cut 50 just for representation. So we can see that there is again deviation. So this diamond red and green circle denotes the result obtained from data, and these thick bars denote the 1 sigma error bars. So we can see that there is always a deviation for L-cut 50 for all these 3 Minkowski functionals, which implies that the field is non-Gaussian at least
5 minutes. Huh?
Yeah, okay, thank you. So here I would like to come to the second thing, which is the deviation from Gaussianity. So as the Scalar-Minkowski functionals, the previous plot that I have shown, it is not actually quantifying the Gaussianity properly. We are using delta Vk. So delta Vk is defined as Vk Haslam minus Vk Gaussian, normalized by the maximum of the Gaussian Vk. So on the left, I have shown the plots. So the red one, the top panel shows the results for U cut equal to 60 Kelvin, and the bottom panel shows for U cut equal to 25 Kelvin. So I'm showing it because in these two distinct masks, the results are getting different. So first thing that I would like to highlight is that if we check the amplitude of delta Vk for U cut 60 and 25, we find that if we go from U cut equal to 60 to U cut equal to 25, the delta value is decreasing, which implies that if you go to more masking, I mean, if you remove the central region more and more, the field is tending to be Gaussian. Second thing is that if we go down, which is L cut equal to 50, 70, 90, again, we find that the amplitude is decreasing. So this means that if we go to smaller angular scales also, the field is tending to be Gaussian. And another thing that I would like to highlight is that error bar for U cut equal to 25 is a little higher because of the lower sky fraction. Now, discussing about the deviation from Gaussianity, I would like to go to the nature of non-Gaussianity. As I have already told you, this delta Vk can actually help us to say something about the nature of non-Gaussianity. So we find that we have actually plotted the from the skewness and kurtosis parameters, we can get the analytical expectation for delta Vk using skewness and kurtosis parameters. So the black lines actually shows those results. So we find that for U cut equal to 60, first order terms contribute less than the second order terms. And delta Vk overestimates the delta Vk from numerics, which is denoted by this red, by a factor of 2. However, the shape roughly agrees. Third thing is that even at higher L cut, this trend is followed. So just for a comparison with what we have shown for the cosmological GNL type of non-Gaussianity, you can see that these shapes are actually matching. So this and again, I would like to go to the U cut equal to 25 case. Again, the trend is followed, the shape is matching, but the amplitudes are decreased a little. Apart from that, the analytical expectation, which is denoted by these black lines as well as the green lines, they are exactly matching. So this means that we have a very good agreement between delta Vk for perturbation as well as the numerical. So apart from this, we have also obtained the chi-square. So chi-square results also indicate that there is a decrement in the non-Gaussianity. But even at L cut equal to 120, there is a 3.3 sigma significance. So these are the takeaways. So Haslam non-Gaussianity is sourced by second order kurtosis terms, and field approaches Gaussian behavior at small scales, and polar regions of the Haslam map can be approximated by a mildly non-Gaussian field. So given the time limit, I would like to briefly stress on the statistical isotropy result. So we have computed alpha for Haslam field, and again we have for these two different U cut 25 and U cut 60. So we have obtained delta alpha for this. So again, the significance of anisotropy, we cannot use the normal chi-square statistics here, since the alpha statistics is not following a beta probability distribution, is following a beta probability distribution. So we have defined a different statistics, just chi tilde based on the median value. And we have shown this chi tilde as a function of different threshold. So we can see that for U cut equal to 60, this chi tilde is negative in all the cases, and chi tilde gets inside one towards a higher L cut. So here one implies this is the 95% region. So we can see that for U cut equal to 60, many of these values are points are away from 1, which implies that there is enough anisotropy in the field. However, if you come to U cut equal to 25, chi tilde is less than 1 and positive across all L cut and most of the threshold. So this implies that if you go to smaller angular scales, as well as if you remove the large scale structures in the field and large scale emission regions, the field is tending to be statistically isotropic. So this is the last slide. So after excluding the warmer regions of the sky, Haslam field exhibit isotropic behavior even at large angular scales, and towards smaller scales, Haslam field becomes more isotropic. So I'd like to come to the summary and discussions. So we find that the overall level of non-Gaussianity decreases as more high emission regions are masked and as we go to smaller angular scales. So this corroborates with the previous results obtained by Ben as well as Rana et al. And our analysis gives extra details that the leading source of non-Gaussianity is the Curtis term, with the skewness term being subdominant. And third thing is that in the cooler regions of the Haslam map, non-Gaussian deviation agrees well with the analytical expectations, keeping up to the Curtis systems. And finally, we find that as the high emission regions are masked and at smaller angular scales, Haslam field is increasingly isotropic. So we have some new directions here. So the Curtis origin and GNL can help us to relate these results to the interstellar magnetic field and the distribution of cosmic rays. And another important thing that I would like to highlight is that bispectrum, which is commonly used as a tool to check the non-Gaussianity of foreground, is not enough, as there could be higher order information. So trispectrum or Minkowski functional can help us to check the details. And we are actually interested to go to Planck high resolution synchrotron maps, and we want to check the physics of synchrotron at different frequency bands. So these maps are given by WMAP, Planck, SPAS, etc. And we are also interested to check the synchrotron intensity as well as polarization maps. And we are also interested in checking the statistics of thermal dust emission, which is another major foreground map. So both in intensity and polarization to study the morphology of galactic magnetic field. So with this, I would like to thank everyone for listening to me, and yeah, waiting for your comments and questions.
Thank you, Fazlu. I mean, we are a little bit, time is little, so 5:15, so we can take questions. Yeah, Desh.
Okay, yeah, thanks. Very interesting. One thought occurred to me, which I'm just mentioning as a comment. You naturally have two hemispheres, or not quite full hemispheres, that you use data over because of the removal of the galactic emissions.
Yes.
You might want to compare the results across the two sectors, and individually you might find that the effect of having taken out galactic emission will be less severe, and comparison might yield some surprise.
Yes.
Thanks.
Yeah, so we are actually planning to do that. So we are planning to do patch by patch analysis. So this includes two different hemispheres as well as different patches in the sky, and we are planning to check these kind of statistics in those patches. So yeah, thank you, Desh.
Prasoon has a question.
Hi. Yeah. Am I audible now?
Yes. Yes.
Okay. So I was asking. So you said that when you go to smaller scales, the Haslam map becomes more like Gaussian. So the smallest scale, where I mean the scale at which it becomes Gaussian, how far is it away from the resolution of the Haslam map?
Yeah, so it's an interesting question. So right now we have checked up to LCAT 120, so which corresponds to around 1.5 degree. But we know that the resolution of the Haslam map is around 56 arc minute, so which correspond to say 180, close to 170 or 180.
So so maybe it will be a good idea to make a mock map and check it. Just because of the resolution kernel, you get a Gaussian pattern at that point.
So map of what? Can you please
if I make a mock map of the sky, like Haslam map, and convolve it with the resolution element, then at what scale I start to see the skewness and Curtis to disappear.
Okay. Yeah, that's okay. But yeah, so the motivation for using Planck maps or other high resolution maps is mainly this. Like we can see like so from what so to what angular scale we can go such that it may get to completely Gaussian, or yeah.
Okay, any other questions? If not, so we come to the end of this session. And I think we thank all the speakers and over to the organizers.
Yeah, thank you all for your nice talks. Now the floor open for the discussion.